Welcome to Science 101. Today's question was sent in by a longtime viewer, Kevin, from Peter Hoy Elementary School. Say hi, Kevin.
Hi.
Kevin's question is, how does stable equilibrium differ from other kinds of equilibrium? Before we answer that question, we'll need a few items. A bowl that's almost completely round on the bottom, a toothpick, a styrofoam sphere, 2 sharpened pencils, erasers optional, some modeling clay, a soda bottle with a cap still on it, and any kind of ball. Okay, not any kind of ball. A round ball, small enough to fit in the bowl and still roll around. That's better. Now let's define equilibrium. You probably already have an idea what equilibrium is. Equilibrium means balanced. You could describe your mood as being in equilibrium. There could be an equilibrium in relations between nations. Or if you fall down a lot, the doctor might tell you your equilibrium is off. Okay, I think you got the idea, son. Don't hurt yourself. Equilibrium in science also refers to balance. The overall water content of the atmosphere is in general equilibrium. Over time, the amount of water evaporating into the atmosphere from the Earth is roughly in balance with the amount of water vapor reaching the Earth through rain, snow, and other precipitation. Here's another type of equilibrium. Get the ball and the bowl. As you know, bowls can't be completely round on the bottom or they wouldn't sit still. So we'll have to improvise a bit. Turn the bowl upside down and place the ball on top. The ball is in equilibrium. All the forces acting on it balance it out and it's not going anywhere. But push the ball to the end of the bottom and what happens? The ball rolls to the flat surface because the forces acting on it, gravity and a force from the bowl, push it in that direction. This is called unstable equilibrium. Moving the object away from its equilibrium position results in it moving even farther from that position. Here's another example of unstable equilibrium. Take the toothpick and stick it in the styrofoam sphere. Now, try to balance it. It's not easy though. When it is in balance, it's unstable. Any slight disturbance, like breathing or blinking your eyeballs, moves everything away from that equilibrium position. Okay, get the ball and the bowl again. Turn your bowl right side up and place the ball in the bowl. Is it in equilibrium? Yep. All the forces acting on it are balanced, and it's not going anywhere. Now, move the ball to the edge of the bowl and let it go. What happens? It rolls back to the bottom. Oh sure, it'll overshoot a few times, but it'll eventually settle back to its original equilibrium position. This is called stable equilibrium. Whenever you move the ball away from its equilibrium position, the forces acting on it, Earth's gravity, and forces the bowl exerts, push it back to the equilibrium position. Okay, one more quick example. Place your ball on a flat surface. If it's truly flat, then the ball will stay where you put it. If you've been paying attention so far, you know that the ball is in equilibrium. It doesn't go anywhere when you let it go. The forces acting on it balance out. Move the ball a few inches away from its original position and let it go. What happens? Well, if your entire surface is flat, then the ball stays in the new position. It doesn't tend to move toward or away from its equilibrium position. This is called neutral equilibrium. Any disturbance from an equilibrium position puts the ball in the new equilibrium position. Most of the really interesting cases of equilibrium in science and technology are examples of stable equilibrium. Let's talk about dynamic stable equilibrium. Dynamic stable equilibrium means that things aren't just sitting still. One of the easiest to understand is the heating or cooling system in your home. Let's say you set your thermostat at 70 degrees Fahrenheit, but don't do this because Mom and Dad will get mad. We'll call that temperature the equilibrium position of your home's temperature. What happens if your home's temperature falls below 70 degrees? Well, that causes physical changes in the thermostat, which trigger your furnace to turn on. Your furnace heats your home until the temperature reaches 70 degrees again, when you're back at the equilibrium position. At this point, Physical changes in the thermostat turn off the furnace. Now, if the temperature of your home rises above 70 degrees, the physical changes in the thermostat might turn on the cooling system, which again would cause the home's temperature to return to 70 degrees. Your home seldom stays at a set temperature. The home's temperature is constantly changing, which is why we call it a dynamic stable equilibrium. Your body has a similar heat and cooling system that's in dynamic stable equilibrium. If you don't think it's dynamic, take your temperature several times a day. It won't be constant. Your body has an equilibrium point of temperature that's somewhere around 97 to 99 degrees Fahrenheit. If your temperature falls below that point, you begin to shiver, which tends to raise your body temperature. If your body temperature rises above the equilibrium point, you sweat, and the evaporation of sweat causes the heat to flow away from your body. The population of animals in an ecosystem is in dynamic stable equilibrium too. There's an equilibrium point of populations of predators and their prey. Hey, you varmint! On a larger scale, like the Serengeti in Africa, when the population of prey increases beyond the equilibrium point, that increases the predator population because more food is available. Increased predator population results in a reduction of the food supply, meaning the population of prey falls below the equilibrium point. That in turn results in a reduction of the predator population, which results in an increase in the prey population, which results in an increase in the predator population, which results in, well, you get the idea. As you can see, stability in science can involve a lot of changing back and forth. Here's a fun example of this. Grab the styrofoam sphere with the toothpick in it and the soda bottle. Now, try to balance the styrofoam sphere on top of the soda bottle. It's still not easy, is it? Okay, now add the pencils and the modeling clay. When you balance this new system, you'll find that it's remarkably stable. Any disturbance causes it to move back to the equilibrium position. The forces from gravity and from the bottle cap create this stable situation. The key is that by adding the pencils and the clay, you move the center of gravity from the styrofoam sphere to below the bottle cap. Now you know why tightrope walkers use long bending poles to help keep their balance. The pole bends below the wire, which lowers the center of gravity and making everything stable. Well, that's all for today. Kevin, I hope that answered your question. It sure did. I learned a whole bunch. What are you planning on doing with all this new knowledge now? I'm going to balance out my pet ecosystem. Are you going to do that by adding more parakeets? Nah, I was thinking a dog.
Meow?